All right, we are recording now. So section 11.5 deals with the chain rule. Now you learned the chain rule back in calculus 1, but that was for a function of one variable. We have to have a chain rule for functions of multiple variables. And the book has a lot of rules and formulas, but if we use our intuition and a good flow chart, we can come up with a chain rule for any type of situation. I'll still show you some portions of the book, but let me give you a moment to copy this example down. Okay. All right. Okay, so let's take a look at this situation here. We're using an applied example to help us get a feel for what the chain rule is. And in this case, we have a voltage, and you don't have to, this is sort of like basic stuff, but you don't have to have taken physics, don't worry. But a voltage in a simple electrical circuit slowly decreases as the battery wears out. I think you all know that happens. And the resistance R is so slowly increasing as the resistor heats up. Now, there's an Ohm's law, V equals I times R. That means that voltage is equal to current times resistance. How many have heard of Ohm's law? Maybe in one of their other classes. Maybe you've seen it. Okay, you've seen it? All right, very good. Well, all right, so using Ohm's law, we want to find how the current is changing at the moment when your resistance is 400 ohms. That symbol is called ohms. Current is 0.08 amperes. That A stands for amperes. The change in velocity with respect to time at that at the moment is negative 0.01 hold on here, volts per second, right? And the dr dt is equal to 0.03 amperes per second. All right, so let's see, how are we going to handle this problem? How are we going to do this? So, well, first of all, let's think about what we're trying to find. Okay, what are we, in other words, what are we looking for? Well, they say they want us to find how the current is changing at the moment when all of this occurs. But if we want to find how the current is changing at a particular moment, we are trying to find what? What are we trying to find regarding the current? We're not trying to find the current. Okay, good, Samuel. We're trying to find di dt. Okay, we're trying to find a derivative, di dt. Now, this situation is different than what you encountered in Calculus 1, because the current is a function of both voltage and resistance. Because look at the formula. Well, V equals I times R. But this means then that current is equal to voltage divided by resistance. So the current I is not a function of just one variable. It's a function of two variables. Now, in turn, voltage and resistance are functions of what? They're functions, I mean, it doesn't end there. Voltage and resistance are functions of what variable? Well, look here, you have dV dt. You have that rate. You have dr dt. If you have dV dt, then V, that's right, Eva, voltage is understood to be a function of time, which makes sense. And resistance is understood to be a function of time in this circuit, right? That makes sense. So we can extend our flow chart here to include T. So this here is the flow chart. And based on that flow chart, we can find this derivative, and it'll be intuitive. So the rate of change of the current with respect to time is dependent on how current changes with voltage and resistance, and then in turn also how voltage changes with time and resistance changes with time. So given that, I go to the next page and I set this up a little formally. And based on, let me put this in blue. Based on this flow chart, here. That's not, we call that a flow chart. Based on that, I can construct my chain rule based on the flow chart. So let's see if this can make some sense to us. How many paths are there in the flow chart? How many paths are there in this flow chart here? Well, current's a function of there. That's right, Norina. There are two. Current is a function of velocity and resistance, but velocity and resistance are functions themselves of time. So the first path here that is correct. That is correct, Yeva. Current is a function of velocity and resistance, and they're both functions of time. So the first path here corresponds to this part of the chain rule. Current varies with voltage, but then voltage varies with time. And you'll notice that when I say current varies with voltage, I'm using a partial derivative for that part of the chain rule. But then when I say voltage varies with time, I use just a regular derivative because voltage is a function. I mean, in terms of this flow chart, voltage is treated then as a function of time. And it's multiplicative. It's multiplicative. The more the current varies with the voltage, the more that's going to affect how current varies with time. So it's a multiplicative effect. Now the other path is this path here. Current is a function of resistance, and then resistance is a function of time. So we take the change of current with respect to resistance, and then look at how resistance changes with time. And the multiplicative effect is the contribution in regards to resistance that contributes to the di dt. Does this make sense, how this chain rule works? Good, good. Yeva's comfortable. And Ashifa's comfortable. Very good. Norina's good. Okay, excellent, excellent. I mean, rather than me just kind of throw a formula at you, so to speak, I like to have an intuitive feel for this chain rule because there's many different kinds of chain rules. Now, we understand that that the current is equal to voltage times resistance to the negative first power, right? So that means when we differentiate the current with respect to voltage, well, we treat the resistance as a constant And so that gives you just 1 over R. And when we take the derivative, the partial derivative of current with respect to resistance, we treat the voltage as a constant. And so that's going to give you the partial derivative, negative V times R to the negative second. Okay, and the second part, this part here, I write that as negative V over R times 1 over R. Okay, but let me just see here. But V over R is equal to the current. Voltage divided by resistance equals the current. And so we end up with this. And now we're able to find di dt by simply taking the information that was in the paragraph and plugging it in for, for every portion of this chain rule formula. dV dt, for instance, dV dt is equal to negative 0.01 volts per second. That was given in the problem. And dR dt, okay, was equal to 0.03 ohms per second. That was given in the problem. And then all the other values also. And so you end up getting negative 0.000031, and the units are amperes per second. They're amperes per second. And so there you've just done the chain rule. Let's see, Samuel. So Samuel is asking about this part here. So the partial derivative of current with respect to resistance is the partial derivative with respect to resistance of the function v times r to the negative first. That's from here. And so if you leave the v constant and take the derivative of r to the negative first, that's going to give you negative r to the negative second by the power rule. And that's how you got this result here. Are you comfortable with that, Samuel? Okay, wonderful, wonderful. Good, good, good. So that's how we get that. Are there any other good questions before we go to our next example? Okay. Let's do another one. Another chain rule problem. Let me give you a moment to copy this example down. Okay, so in this problem, let's see, we have that u, this function u, well, it equals x to the fourth times y plus y squared times z cubed. And then we have x and y defined as you see here, x, y, and z defined as you see here. And then it wants to find the partial derivative of u with respect to x. Now notice they're not saying du dx. They're not asking you to find the regular derivative of u with respect to s. Why would that be? Well, let's look at a flow chart. Let's look at a flow chart here. Flow chart will help us a lot. So here we start out with u. Okay, this is our function, right? Okay, and let's see here. U is a function of how many variables? Three. Good, Lexi. Good, Yeva. X, Y, and Z. U is a function of X, Y, and Z. Now, the next level of our flow chart, we have to ask ourselves, what is X a function of? How many variables is X a function of? Is it just one? Is it two? Is it three? That's right, three. That's right, Yeva. That's right, Lexi. R, S, and T. One moment, class. Okay, let me continue here. So, okay. So, does du ds exist? Well, u ultimately is a function of what? Based on this flow chart here, u is ultimately a function of what? What variable or variables? That's right. R, S, and T. Good, Lexi. So you can't say find du ds because u is a function of three variables, not just one. Three variables. So that's why they say find the partial derivative of u with respect to s. Let me ask you, well, are there any questions on that? I want you to be comfortable with notation and everything. All right. Well, based on this flow chart, how many, if we're gonna write the chain rule for the partial derivative of u with respect to s, how many links are there in our chain based on this flow chart? Based on this flow chart. Well, Norina, that it would keep us pretty busy if it had 9 links. But I appreciate your response. I mean, I like it. There's no bad answer here, no. But actually, it's going to be 3. Now I know, Norina, why you're saying 9. Okay, okay. And so Lexi and Norina were the brave ones here. They answered. But you're all brave here at one point or another. There are like, well, think of it like this. We want to know how u changes with respect to s. So the paths that we're interested in, I want to say this the right way. U changes with respect to x. Okay, of course. And then how does x change with respect to s? That's one of the paths. The variable u also changes as y changes, and y changes as s changes. That's the second path. And then u changes as z changes, and z changes as s changes. That's the third path. Norina, does that make good sense? Why there are 3 paths? Good, good. So now what we have to do is write the chain rule. If there are 3 paths of variation, there are 3 links in the chain. There are 3 links in the chain. Now, what I'd like you to do is take a moment on your paper and write down what you think the chain rule is for this problem, and then I'm gonna show it on the next page. just write what you think what the chain rule is for this problem based on the flow chart, and then I'll show you on the next page. Okay, here we go. Okay, so here is the chain rule for this particular problem. Who got that one right? Who did get that one right? Okay, Simon had got it right. Okay. Lexi did. Okay, very good, Simon. Very good, Lexi. Very good, Aura. Samuel, Norina, excellent. Yeah, so you see here, the based on the three paths, again, if I highlight the paths here, you know, here's the one path, and that corresponds to this part of that link in the chain rule. And you notice we're saying we have partial derivative of u with respect to x, because u is a function of x, y, and z. But x is then a functional of three variables as well. So we multiply by the partial derivative of x with respect to x. That is not ds. No, hold on. That is not dx ds. It's the partial derivative with respect to of x with respect to s. Okay, and then the second path. Here's the second path. That corresponds to this link in the chain. U changes with y, and then y changes with s. So ultimately, if we want to know how u changes with s, we take the rate at which u changes with y and multiply it by the rate at which y changes with s. Okay. And then the last path is this path here, and that corresponds to the third link in the chain. And then naturally, based on the definitions of u and x and y and z, we come up with that the partial derivative of u with respect to s equals all this here. Now you'll notice that you know, and I mean, you know how to take partial derivatives. I trust everything's okay here for you. But you'll notice that well, I want to say this the right way. You'll notice that, like for instance, the 4x cubed y. Well, I could substitute in for that portion of the formula. I could put in x equals r times s times e to the t, and then y would be r times s squared times e to the negative t. Okay, but I'm not going to do that. I'm not going to break this term down either, and I'm not going to break this term down either, because I'm trying to evaluate this partial derivative specifically when r equals 2, s equals 1, and t equals 0. So all I need to do is, for those values of r, s, and t, all I need to do is compute what x is, what y is, and what t is, and then substitute that all in this formula here. So x is 2, y is 2, z is 0, and then of course, well, hold on, no, wait. Yeah, x is 2, x is 2, y is 2, and z is 0. And so, like, how do I get 64 here? Well, 64 is 4 times 2 cubed times 2. Okay, and then the times 2 part, well, x is equal to, no, wait. Yeah, r times e to the t here is just 2 times e to the 0. And that's how you get 2. So, and so just, I'll let you copy it down. I think it's pretty clear what's here, but just let me know if you have any questions. Are there any questions on, so we end up getting then, in terms of notation here, the partial derivative of u with respect to x, that partial derivative, evaluated when r equals 2, S equals 1 and T equals 0, that equals 192. So at that instant, when R equals 2, S equals 1, and T equals 0, this function is, the rate it changes with respect to S is equal to 192 units. Absolutely fascinating. Are there any questions at all about how I got that answer? I mean, I tried to put some details in here for you, but are there any questions? Is anything unclear? Okay, give me a thumbs up if you're good, and then I want to go to the ebook for a little bit. All right, Narina's good, Mary's good, Angela's good, wonderful. Matthew's good, Arian's good. Yeva's good. All right, let me bring up the ebook then. Samuel's good. Okay. Alexander's good. All right, excellent. All right, well, let me bring up the ebook. I'll show you just a few things here in the ebook. So section 11 point, well, hold on here. So section 11.5 is the chain rule for functions of multiple variables. And the way the book has it, like here for they call it case 1, we actually did that case, only we had current, instead of Z as a function of X and Y, we had current I as a function of voltage and resistance. But chain rule we got was the same basically as this one. So again, you know, they give a scenario, they give a chain rule, and if the flow chart's there, you know, it's easy to see what the chain rule is. So there's different chain rules based on different situations. Like let's say, for instance, you had, let's look at a rule. I'll tell you what, let me do one with you on the whiteboard here. Or I'm going to let's say that you had, Z was a function of X and Y. Okay. And let's say X is a function of S and T, and Y is a function of S and T. Okay, so can you do the flow chart? Can you do the flow chart? And then, based on the flow chart, can you do the chain rule? Let me give you a moment here, and then I will follow along here to help you. Well, to see if you're, you know, let's see what you come up with, and then we'll see if you're right. Okay, so flow chart should look like this. Whoops, we have an error here. One moment. Okay. And then, I'm sorry, I should have told you, I want the chain rule for this, the partial derivative of z with respect to s. Who got the flow chart right? Hopefully all of you. And there are two rules, right? Partial derivative of z with respect to s and partial derivative of z with respect to t, right? Two rules. All right, so who got the first chain rule correct? Partial derivative of z with respect to s. Okay, wonderful, 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 wonderful. Okay. All right, then let me give you a little bit of time here to get the second chain rule. All right, who got the second chain rule? Who got that one? Wonderful. Eva got that. And Angela, Narina. Wonderful. Okay, so if we go to the book then, if we go to the book, so these are the chain rules for that, for this, what we just did. So, you know, you don't have to memorize these chain rules. You just draw the flow chart. And once you draw the flow chart, you're in business. You're in business. Now, these chain rules deal with first partial derivatives. What if you wanted a second partial derivative? Well, second partial derivative, I can tell you, is it's complex. It is complex to do, um, and they have it. I have it actually. Well, I'm gonna just go to example 7 in the book. I want to show you one example of where they do a second derivative, second partial derivative using the chain rule. Okay, let me go to the book for that. One moment. Okay, so here you have a function and it has second order partial derivative. We want to find, well, x is equal to r squared plus s squared, y is equal to 2 times r times s, and z is a function of x and y. And it's no problem finding the first partial derivative. The second partial derivative is going to take more effort. And I just want to take you through the steps. There is a problem in your homework that deals with this also, but it has a watch it video. So it's not like you're going to get a lot of these kind of questions. Okay, just one, I believe, on your homework. But let me just take you through it here briefly. So, all right. So if we want the partial derivative of z with respect to r, we could draw a flow chart, and the flow chart would be, well, actually, we just did one like that, right? We just did one like that, right? Except x and y were functions of s and t, but you know, it's the same kind of thing here. There's the chain rule, and that your answer is going to be the partial derivative of z with respect to r is the partial derivative of z with respect to x times 2r plus the partial derivative of z with respect to y times 2s. Okay, so based on how x and y are defined, the partial derivative of x with respect to r is just 2r, and the partial derivative of y with respect to r is 2s. But now what we want to do is we want to find the second partial derivative of z with respect to r. So we have to take this highlighted formula here. We have to differentiate that with respect to r. Okay, we have to differentiate that with respect to r. And you'll notice that in the formula here, you have partial derivatives of z with respect to x and z with respect to y. Well, one thing you have to recognize is that, like for instance, the partial derivative of z with respect to x is itself, since z is a function of x and y, its partial derivative would be a function of x and y, and x and y are in terms functions of r and s. And similarly, you could draw another flow chart for the partial derivative of z with respect to y. And so, I mean, we will get there, but again, okay, let me just highlight this. And let me make that bigger. Okay, so see, I feel that this could come up later in your life, and you should have an idea of how to handle it. A second partial derivative using the chain rule. So, all right, so the highlighted formula there in yellow, we differentiate that with respect that partial derivative with respect to r, and we get the second partial derivative of z with respect to r. So that means, you know, you take the partial derivative of the right-hand side with respect to r, And then you're going to utilize the product rule. Okay, you're going to utilize the product rule. So the derivative of 2r is equal to 2 with respect to r is 2. You leave the partial derivative of z with respect to x alone, and then you leave 2r alone and take the partial derivative of that partial derivative with respect to r. Then the last entry in the highlighted box, you take the partial derivative of 2s with respect to r, that's 0. That's why there's no term there for that. And then the last part of the product rule is 2s times the partial derivative of that partial derivative with respect to r. And so now what's left to do is you have to recognize that the partial derivatives of z with respect to x and y, we can create flowcharts for them as well and apply the chain rule. And when we do that, okay, let me just see if I can highlight. When we do that, we're going to get these two formulas here. It's a lot of work. It's a lot of work. But let me just see if there's anything I can. Yeah, so what they're doing there is they're doing a chain rule for based on flowcharts for the partial derivatives of z and x. No, based on flowcharts for the partial derivatives of z with respect to x and y, they are writing out the chain rules. And then they just basically, since you know the definitions of y and x, they then write out the formulas. So you're going to have to look at it a little bit, but I'm just trying to illustrate to you what they're doing, so that you have an idea here. And then based on those chain rules, they substitute the chain rules there, the two chain rules in the highlighted box. I want to say this right. Yeah, they substitute them back in the yellow formula there, the formula highlighted in yellow. And when they do that, they end up getting this result below. And that's what's going on. That's what's going on. And then you have your final answer at the bottom there. So that's just a guided tour of what they're doing. And you have one problem in your homework where you have to find a second partial derivative of a function with respect to a variable. And there's a watch it video, and you'll be fine. But I think about you in your future. Maybe you're taking an engineering class, maybe some science class, and you have a function of several variables. Maybe an econ class, function of several variables you might have, and you need to take the second partial derivative using the chain rule. You ought to have an idea of how it would work. And okay, are there any? I'd like to, I think, give you some time here to work on this section 11.5. Are there any questions at all before I stop the recording? Give me a thumbs up if you're reasonably okay. Reasonably okay with section 11.5. Good. Yeva's reasonably good. Matthew, Angela, Marina, Lexi, wonderful, wonderful. And let's see, hold on here. All right, Aura and Alexander, good, good. Okay, excellent. All right, I will stop the recording. And Arian, very good. Arian, I got you in there at the end. Excellent.